Welcome to another exciting presentation about artificial intelligence and its neural networks. Today I am going to speak about an attempt to make analogy-based reasoning mechanisms usable for dealing with artificial neural networks. Nevertheless, if I'm dealing with a LEGO EV3-based AI-instructed Industry 4.0 simulation system, if I'm dealing with a variant of Fisher Technic's training system, or if I'm dealing with a real-size simulation system of the Center for Industry 4.0 in Potsdam, each of those simulation systems shall enable different socio-economic scenarios with humans, techniques, and organizations in Internet of Things and Industry 4.0 context. In the one scenario, artificial knees are produced. In another scenario, car wheels are produced or chocolate bars. So, dependent on the current scenario simulated, the current instance of a machine or workpiece in that scenario changes, and its current state, role, and activity therefore can be visualized by one of the displays you can see on the picture. For instance, in the one scenario, a certain machine can represent a milling machine, and in another scenario, the same machine can represent a quality station. Principally, its physical system elements all consists of machines that carry out the one or other production task, conveyors that transport workpieces from one machine to another, and workpieces that represent the products that are routed via conveyors among machines and so get produced task by task. However, each of the system's elements are integrated within the Internet of Things and so can be considered as cyber-physical system. Therefore, each of those system elements has its own set of sensors perceiving the environment of the system, has its own set of processors deriving decisions, for instance with the aid of artificial intelligence, and these artificial neural networks, has its own set of actuators carrying out decisions to manipulate its environment, and has its own set of communicators for sharing the individual ANN-based knowledge. One can say the simulation system elements need to be considered as knowledge carriers having individual ANN-based knowledge. Further, as each system participates in a network of cyber-physical systems, each has its own perception and creates an individual data collection. Each is continually learning on the basis of this collected data, and finally, each individual knowledge carrier can evolve. Thus, the research question is, how can continuously improving ANN knowledge bases be examined experimentally? So summing up, let us assume to have one of these simulation environments or production systems, enabling the use of different kinds of AI techniques, bringing in human test persons, collecting data about organization and individual artificial neural networks and knowledge bases, and that enables us to carry out interesting experiments. So in the following, I try to clarify how to enable each of those individual machines, for instance, to apply ANN for task realization, to provide its ANNs for neighboring systems, to get knowledge from following systems, and to create ANNs even though the individual workload and processing performance is not sufficient. So far, and to the best of our knowledge, research approaches have focused on training of ANN and continual learning environments. We have these awesome programming libraries enabling the training of ANN. We have some Industry 4.0 simulation systems, but only one considers AI to be instructed. And has ANN knowledge bases. There are some concepts and designs addressing the efficient distributed task realization with the network infrastructures, but what about the creation and provision of ANNs? None of those enables the flexible dealing with ANNs that are characterized and selected by analogy-based learning procedures which I am aiming to demonstrate in Industry 4.0 simulation systems. So the today's talk and the underlying paper contributes by a learning approach that supports the identification of knowledge of ANNs and the corresponding management of those packaged knowledge bases. You can say it intends to address the intentional management of ANNs, its knowledge as part of a new knowledge management. How have we proceeded? We have followed the procedure of implementing AI-based systems using the concept of neural modeling. Initially, we have brought stakeholders on the same page. We have agreed on target and requirements about Industry 4.0 systems dealing with ANNs. Then the technical conception and design of AI-based case-based reasoning for ANNs has been drafted. About this I'm going to speak today. So I'm going to speak about a conception that is currently at implementation. And the corresponding ANN-based knowledge bases are set up, trained, and collected for runtime operation. So let's focus on the design. Let's start with the traditional case-based reasoning cycle and the current problem. From a collection of cases, the so-called case base, cases are retrieved that shall give a solution to a target problem. Hence, a case consists of a problem, its solution, and annotations, such as the solution's performance. Thus, cases whose solutions have been proven in similar problems are attractive. If an attractive case has been selected, it will be used for the target problem. After applying the previous solution to the target situation, it is tested if the case shows good performance at the device it has been assigned. When the solution has been successfully adapted to the target problem, new insights and experiences are stored at the case base, so that the case is available for successive CBR cycles. How can this cycle be transferred to the ANN domain? How can we enable these learning mechanisms to deal with ANNs, provide ANNs, preserve good performing ANNs, etc.? Initially, there is a need for ANNs. In this research, solutions refer to ANNs that shall be considered by a specific simulation device. So, based on a problem description, a case is selected that shall help to overcome a problem. The attractive ANNs that have been useful in similar scenarios are prepared to be reused. This might include an adaptation of the ANNs so that the ANN can be faced with sensor data from a specific device. It is tested if the ANN shows good performance at the device it has been assigned. If required, a new ANN solution is created, which either means the training continuation of pre-trained ANN, so the modification of former solutions, or the setup of untrained ANN, creating a brand new solution. However, scenario-specific data comes directly from the device the ANN has been assigned to. When the ANN has successfully been adapted to the target problem, new insights and experiences are stored at the case base, so that the ANN is available for successive CBR cycles. This might refer to an evaluation of the ANN's goodness of performance in particular simulation context. How to formalize this idea? We are starting with a specification of R, the set of problem situations, as well as S, the set of solutions for a certain situation. These are described by the set of D, the set of description dimensions. For instance, some candidates can be the ones that you can see here. For instance, let's face dimension D5 if an ANN is available that already has dealt with temperature data. It might be more likely to be useful than ANN candidates dealing with milling speeds. Let's further face dimension D2. if an ANN is available that already has been used in the same scenario, it might be more likely to be useful than ANN candidates from another scenario. However, we set up the possible problem description by the cross product of R and D. Similarly, we specify the solution description. Then we can set up the CBR problem statement by the pairwise characterization of the problem and the corresponding environmental description, and the CBR solution by the pairwise characterization of the solution and the corresponding environmental description. So the common CBR case specification can be used to set up the AI case. Using this case, we can specify the optimization problem. It's finding the one case that fits best to the current problem. In this example, this case minimizes the function f. For instance, when dealing with the real numbered values only, the function can indicate the goodness of fit by minimal element-wise deviations. But how can we design an architecture that enables the AI case-based reasoning mechanisms? Let's focus on one kind of system that you can see on the left of the picture, and its architectural embedding within the networked infrastructure on the right. The Raki simulation basis environment. This kind of component deals with the physical machines of the simulation system. For instance, it presents videos on the displays, starts conveyors, etc. Please note, the individual machines communicate via a global communication server with other physical systems. The Node-RED environment. This kind of component provides relevant data for the current scenario. When sensor data without unit is perceived by the physical machine instance and communicated via the server, it is mapped to the current scenario context. For instance, it is interpreted as a temperature value. Further, on the basis of the machine's current problem description, following a certain knowledge-based selection strategy, the best AI case is identified. Please note the interaction channels. Cases are either collected locally, at neighboring machines of the Raki environment, at the edge component, which is a more powerful computing unit and storage unit, or at the AI cloud component, like Amazon, Google, or external services. Finally, the AI simulation environment. This kind of component deals with AI case solutions. It loads ANNs, activates them by the Node-RED environmental data, generates ANN replies, and communicates them back, so that the Node-RED environment can remap the results for the physical machines of the Raki simulation environment. So let me ask a rhetorical question. Can you identify redundant elements? Once implemented and provided as a Docker container, the same components can be started on every node. So you can identify the Node-RED environment at the edge component and the cloud component, and further Raki machines and elements. You can identify the AI simulation basis environment on these kinds of devices as well. So, once implemented, it's scalable, maintainable, manageable, updatable, etc. As ANNs have been packed as AI cases, these can be used at any kind of node. But how can we demonstrate this kind of setup? Let's make the ideas more concrete and face one example for this. In the picture, we see the human worker who is collaborating with an AI system. The latter is in charge for product quality control via a photo camera. There's this apple and the AI needs to decide about the apple's quality. In this example, indeed, a stream of fruit arrives at the quality control station. Each piece of fruit is perceived by the AI system's camera, and the ANN-based application is asked to check whether the apple is in order or not. As we are checking for fruit, so that we have to recognize the specific type of fruit, as well as the current quality of that piece of fruit. How can this scenario design be suitable in experiments to demonstrate the AI case-based reasoning? Principally, the CBR cycle is carried out at each AI request and each device. Hence, the machine dialog can look like this. The machine can ask, has anyone a better knowledge base for checking this fruit quality than me? And another device can answer, I have a better ANN, but you might refine it by the cloud or more powerful devices. So looking from the top, facing the ground plan, we have these three different kinds of machines. One, two, three. Each providing user interfaces. In the basic setting, these are equipped with the same knowledge bases, so knowledge about oranges, apples, and bananas. In this kind of setting, we can detect a reference performance of the joint cyber-physical production system. Now we stress this setting by four kinds of scenarios. We are worsening local knowledge base. Here we can simulate in how far the AI case-based reasoning is able to identify neighboring knowledge bases and use them. We are changing the simulation scenario. For instance, we can experiment how to manage knowledge base collections over all scenarios and map and remap these data streams. Maybe we shall separate each knowledge base scenario-wise. We can challenge the joint performance by the need of ANN training. Can the training be performed locally? Shall it be executed at the edge or cloud component? What about costs of those different levels? More powerful computing levels? Or more storage size at these levels? Where to store cases best? When dealing with distributed ANN requests within this kind of networked infrastructure, how to deal with requests best? How to delegate tasks and provide results back? Since AI cases and its applications are designed to be node independent, the AI case-based reasoning for ANN supports the flexible and efficient realization, and we are enthusiastic to carry out experiments on this. Let's come to a conclusion. Summarizing up to here, we have seen a new concept for establishing ANN collections, which become manageable by analogy-based reasoning mechanisms. We have seen a design for an experimental setting addressing fruit quality control, and an AI adequate architecture and its use cases in IoT and Industry 4.0 context. In simulations, the cases are controlled by the goodness of fit and evaluated by the performance, such as total cost, total time, etc. What does this imply for AI-based application systems? The AI case-based reasoning is contributing as a mechanism for a controlled AI-based application system development that establishes and uses adequate ANNs. Hopefully, I was able to clarify the need for further kinds of ANN request mechanisms that allow the AI's knowledge base to be created efficiently. Here I am speaking about ANN distribution and realization strategies. Further, the AI case-based reasoning is contributing as a mechanism for a sustainable training of managed AI knowledge evolution in application systems. So let me come back to the initial research question. How can continuously improving ANN knowledge bases be examined experimentally? As an attempt for an answer, let me conclude like this. As ANN-based knowledge bases have been prepared as case-based solutions, we are now able to research how to realize them with network infrastructure and Industry 4.0 simulations. At least we have a design for examining the evolving ANN-based knowledge bases, and I am enthusiastic about experiments about this. So thanks for having a look on this.